Welcome back, everybody. Now we're going to get into those bone markings. We've talked about what bone is, so now we're going to look at bone markings, parts on the bone where either muscles are attaching or areas where we might have movement of blood vessels through the bones. Because remember, bone is living tissue and it is highly it's constantly building up and breaking old material down. So it's very dynamic. That's the word I want to use. So if we go to the next slide, it gives us some information on the different types of markings that we have. There we go. So here we have regions of the bone where either muscles or ligaments might attach. So a tuberosity is a rounded projection. A tuberosity, the one I typically think about is, and it's not showing on here, is the tibial tuberosity, but here you can see an ischial tuberosity. There are crests. There's an iliac crest. Trochanters, we only see these on the femur, so we have a greater and a lesser trochanter. Lines can be found on different bones. Linea aspera is found on the femur, but you don't see that actually on here because it doesn't show that one, sorry. Tubercles, small rounded projections. Epicondyles are raised projections typically on the lateral or medial aspect of the condyle, and it's above the condyle. The spine is a projection off the bone, and a process is just a bony prominence that sticks out of the bone. So here's the spinous process right there. The head is the expansion that is carried on the neck. So here you can see a head, and then there's the neck right there of the bone. A facet is a part of the bone that actually attaches to another region. So the head attaches typically to another bone at an articulation. A condyle is a large rounded projection. And a ramus is a region of the bone, kind of an arm-like part of the bone, okay? We have depressions and openings, which allow for nerves and blood vessels to move through. So we have grooves, you can see that on the mandible. Fissures are very slit-like openings. Do I see a fissure? Yep, the orbital fissure. Foramen, these are rounded or oval openings that allow for blood vessels and nerves to move through. Meatus is a canal or a tunnel. Oftentimes we use canal versus meatus. A sinus is a very hollow region of the bone, so you can see that right there. Typically lined with a mucous membrane, helps to decrease weight and all these other things. And then we have fossa, which are depressions within the bone that allow for bones to articulate more effectively. So now let's look at the bone structure on the microscopic level. So we've looked at the large structure of bone. Now let's look at the microscopic level of the bone. So here we're looking at bone itself, and we're going down to the more microscopic level. So when we look at compact bone, they are found in structures called osteons or haversian systems. Within an osteon, you can see the little yellow structures there. Those are tiny little areas called lacuna that the bones sit in. These lacuna are found in concentric circles called lamellae. And so here we're just pulling those lamellae out so you can see them a little bit better. We're gonna, in the middle, I'll show you that really quick. You see blood vessels and nerves that run through. In fact, they run through these perforating canals as well as through these central canals. Perforating canals are also known as Volkmann's canals, and the central canal is called a haversian canal. So it's highly vascular and has a lot of nerves running through, sensory nerves that run through the bone. So if we look closer, osteocytes are the bones that sit within those tiny little lacuna that I talked about, those little yellow structures. And lacuna are the cavities that house the osteocytes. Osteocytes are mature bone cells, and they are what produce or what maintain bony matrix. And then remember, lacuna are found within those concentric circles called lamellae. There we go. The Haversian canal is a central canal that carries blood vessels and nerves to each osteon. The osteon is the bone unit that contains that Haversian canal, as well as all those little osteocytes within the lacuna found within the lamellae. And the blood vessels move in through the dense irregular connective tissue wrapping called the periosteum, and they move in through those perforating or Volkmann's canals. Here you can see the little tiny bone cells in those lacuna, and look close, you can see tiny little canals radiating from one bone cell to the next that allow them to talk with each other. Here is an osteon, and you can see that lacuna. A lot of times when we look at bone, it reminds us of what a tree looks like when it's cut down, because you see multiple rings. So bone cells talk to each other, and they help to maintain that the health of our bone. And they talk to each other through those little canals called canaliculi. So that's how they're able to interact, send signals, chemicals, stuff like that. And then I talked about those perforating canals, which are the ones that carry the blood vessels and nerves into the bone and from one osteon to another osteon within the same bone. And you don't see those perforating canals here, but you can see the canaliculi again. So bone is very, in general, it's much more lightweight than you would assume it would be. But it's very strong. It's one of our strongest connective tissues. Bone and cartilage are two of the strongest connective tissues. So bone has organic material as well as inorganic. The organic material formed by your bone building cells called osteoblasts. They form collagen fibers, lots and lots of collagen fibers. Collagen is a very strong connective or a strong protein fiber, but it also has slight flexibility, so your bones have a tensile strength. And think about it. Have you ever had a child jump onto your lower leg? Say they jump on, they want you to bounce them up and down. So they jump onto your shin, right? And that hurts initially, but your bone doesn't break. Well, it allows for slight bending or slight flexibility so that your bone doesn't break that easily. That's what collagen does. Calcium salts, on the other hand, make bone very hard. So calcium, once we have the collagen fibers, we have this flexible bone tissue, then calcium and phosphate come in, so that's the calcium salts, and deposit within that collagen and produce a hard, rigid structure. And so together we have very strong, hard, yet slightly flexible bone tissue. And so the term for bone formation is known as ossification. And this occurs during fetal development, but it also occurs throughout our life. until we hit adulthood. And then we're going to be remodeling our bones for the rest of our life. So there are two major phases for growth of long bones or bone formation in long bones. Um, so the first phase, uh, all of our long bones start out as um, cartilage models. Hyaline cartilage is what forms our skeleton in the fetus. And then as we are getting ready to be born, the hyaline cartilage is going to be taken over by bone tissue, osteoblasts. So osteoblasts start producing osteoid or collagen fibers, so that organic material, and that takes over the hyaline cartilage. And then once that happens, once we have the entire area overtaken by bone, then we have osteoclasts in the middle of that bone are going to break away that middle cartilage region, forming that medullary cavity. Bone is heavier than cartilage. If our bone was completely solid, we wouldn't have the ability to move our body the way we do. And so here we have that embryo where we have just that cartilage model. And then during development, we have bone forming around the edges. We maintain hyaline cartilage on the ends of our long bones and in a region known as the epiphyseal plate. So that's what these areas are, okay? In the middle, bone takes over in that diaphysis or the shaft, and then osteoclasts, those bone breaking cells, break down the cartilage and form that medullary cavity. And so here's a child that still has the epiphyseal plate of cartilage, which allows us to grow in length. And then, of course, we have the articular cartilage on the ends. So interstitial growth is growth in length. And in general, by birth, all of the cartilage is converted to bone, except for at the articular region, so at the ends of our long bones, and at the epiphyseal plate. So we're constantly forming new cartilage at the epiphyseal plate, and old cartilage is being replaced by bone. And so as the new cartilage grows, old cartilage gets broken down and bone replaces it. And this is how we grow in length until the bone overtakes the cartilage, and then we just stop growing in length. That's when we hit our adult height. Appositional growth then is growth in width. So think about a newborn infant. They have very, very, very tiny, thin arms and legs. The bones in their body are super small. There's no way those bones would hold an adult structure. So if we only grew in length, those bones would be really, really skinny, and they'd probably break under the weight of our muscles and other connective tissues. So we grow in width as well, and this is termed appositional growth. So what happens is osteoblasts at the edge of the periosteum produce new bone, while osteoclasts in the medullary cavity break down old bone. And this allows us to thicken our bone, but not make it too heavy for us to move. Once we hit adulthood, and even throughout our entire life, we're constantly remodeling bone. The bone that we have today is not the bone that we were born with. We have remodeled those bones, broken down all that baby bone, and formed new bones. So we're constantly producing new skeletons. So just like your spiders, when they grow, they remove their exoskeleton. We don't remove our inner skeleton, but we break down the old bone and replace it with healthier bone all the time. There are two factors that lead us to remodeling our bones. One is the level of calcium. So we have to maintain a certain level of calcium in our blood. If we have too little or too much calcium, that can cause all kinds of problems with our nervous system and with our muscular systems and our cardiovascular system. The other is the pull of gravity on our muscles. So the pull of gravity is going to determine where bone needs to be built up, broken down and built up, a healthier bone. So if you're putting a lot of stress on your arms, then your arms are going to have to get thicker. Makes sense? If you put a lot of stress on your legs, they're going to have to get thicker. That's what the pull of gravity and muscle on your bones does. So let's look at calcium regulation. The major hormone that stimulates or that maintains calcium levels is parathyroid hormone. This hormone is released throughout our entire life. And in general, it's released when calcium levels are low. We don't have a lot of reason to have high calcium levels, but in childhood, there is another hormone that's released for high calcium levels, which I'll talk about in a little bit. Parathyroid hormone is released by the parathyroid glands, which sit on the posterior aspect of our thyroid gland. And what parathyroid hormone does is it activates osteoclasts, so those are those bone breaking cells. Osteoclasts then break bone down and release the calcium into our blood. If we have a lot of calcium in our blood, then calcium is going to be moved back into our bone, and that is typically associated with calcitonin, another hormone. So this is something I made in my other class, and I'm going to use it here because I think it's perfect. So you remember our homeostatic mechanisms. We have positive and negative feedback. So there are multiple variables that have to be maintained within a very minimal region. So calcium levels is one of those. So we have to maintain calcium levels. If our calcium levels drop too low or get too high, then all kinds of bad things can happen. And so if our calcium levels get too high, this would be mainly, you're looking at children, young children. Calcitonin is the hormone that's released. Calcitonin is released by the thyroid gland, and it pushes calcium levels back to the optimum by causing bone building cells, osteoblasts, to start making more collagen fibers, more osteoid. This allows calcium to be able to settle into the bone, making hard, strong bone. If calcium levels go too low, this is when parathyroid hormone works. So parathyroid hormone decreases the amount of calcium, or decreases the amount of bone calcium by causing bone breaking cells, osteoclasts, to break bone down, and that releases the calcium into our blood, bringing our blood calcium levels back to normal again. So these are both negative feedback mechanisms that push us back to homeostasis. I'm going to stop here and we'll talk about fractures in our next video. All right, bye.